Okay, this next chapter we're actually be looking at the inverse of derivatives. So every function has an inverse, something that undoes what we've just done. So since we can now take derivatives, we have to be able to undo them and get back to our starting point. So the thing that undoes a derivative is called either an antiderivative or an integral. Antiderivative is kind of what they first started out being called, and then later they were called integrals. So we're going to start this chapter just by looking at some real basic antiderivatives, and then we'll move up and see some applications and kind of why these are important, and then we'll look at some other techniques to solving integrals. All right, so let's say we've got something like this. If I know the derivative of a function is 2, what could that function be? Well, I know that in order to get 2 as a derivative, that means I must have 2x, because if I take the derivative of 2x, I get 2. But this is not the only answer that would give me 2. Okay, what if I had y equals 2x plus 6? The derivative of this is also 2. If I had 2x minus 89, I would still have a derivative of 2. So we need to incorporate the fact that any constant could be trailing along on the end of our antiderivative. Okay, because anytime we take an antiderivative, there could possibly be a constant in that original function. So what we do is we use c, capital letter C. That's our constant of integration, and it's always added on to the antiderivative to form the general solution. So when we take an antiderivative and we put this big plus c on it, we're getting a general solution, and if we want a particular solution, we're going to have some kind of initial starting point or at least one point on our original function that we want to cross through. So we've got some notation differences here. Okay. Usually we had this. This is derivative form. So dy dx. Okay, so if the derivative equals some function, okay, because now we're not going to have it be f prime. It's going to equal some function. Okay. We're going to change this into differential form. When we get into integrals, it's important that we have this dx in there. So all we're really doing is we're moving the dx over. It's not true in the way that algebra would make it true, but it's just a more convenient form. This is actually the form that Leibniz preferred, this dy dx, and he spent a lot of time making notation kind of his priority to make sure that calculus was a little bit more close to algebra in its notation. So if we integrate both sides of this, okay, this is a sign for an integral. It's kind of a extended s, I guess, depending on how you do it. So if we integrate both sides of this, if we integrate dy, we get just y. And if we integrate fx dx, then we're going to get a different function, capital F of x, plus our constant of integration, so plus c. Right, and this is kind of the basics of what we're doing when integrating. We're undoing a derivative. These are antiderivatives. So let's look at some rules for antiderivatives, or rules of integration. These should all make sense. If you look at the right-hand column here and think, what if I took the derivative of that? The derivative of it should end up being what's over on the left. Okay, because these are inverses. So if you derive the right, you should get the left. If you integrate the left, you should get the right. So if I integrate 0, I get some constant, because the derivative of a constant is, of course, 0. If k is a constant, some integer, if I integrate it, I get k times my x value plus c. Okay. If I have a constant times some function, okay, it's kind of the same rule that we've repeated over and over again. You can take that constant outside, just like when we're deriving. You know, if I am taking the derivative of 5x squared, I can put that 5 outside. and just derive the x part if I want. So this is kind of the same constant rule. If we are adding or subtracting two different functions, we can split those up and give them each their own integral. And here's kind of the reverse of the power rule. If I'm integrating now x with a power on it, usually when we derive, we drop the power down by 1, which means when I integrate, my power has to go up by 1. Okay, so my n is going to increase by 1. And when I derive, the power drops down. If you notice, I don't have any coefficient here. The only way that I'm going to not have a coefficient, let's say, okay, if I take the derivative of this, the 3 would drop down and leave it just x squared. Okay, so if I want to integrate something that does not have a coefficient, in order to not have a coefficient, I must be dividing by whatever my new power is going to be. So that's why we divide by n plus 1. And then we put our plus c on there. Okay. So these rules are all on page 250 of your book. There's also the trig rules. I didn't list them all out here because basically if you think of what the derivative of a trig function is, if you can integrate that, you'll get the integral of it. So for example, if I integrate negative sine of x dx, okay, I took what derivative in order to get negative sine of x? Well, that means I derived cosine x, because the derivative of cosine x is negative sine of x. Okay, that means the integral of negative sine of x is cosine of x. Another example would be if I integrate secant squared x dx. Well, what do I take the derivative of to get secant squared x? Well, that's tangent x. Okay, so these are some of the trig rules. So let's go through a few examples. So general solution, okay, that just means I want a plus c on it. So I'm going to integrate this, all right? So this is the integral power rule, which means my power is going to go up to 4, okay? So I know that I'm going to have a 4th power. Okay, I can take this constant outside if I want, so this is one way to do it. I mean, some of you guys might see right away what this is going to be, but I'm going to take this outside here. So if I just integrate this part, I'm going to have this over that same number here. Okay, and then I'm bringing the 4 back in, and now when I bring it back, I get just x to the 4th. Okay, and maybe you saw that right from this, because of course if you take the derivative of x to the 4th, you get 4x cubed. But this is kind of how you can incorporate your constant rule and your power rule. The integral of cosine of x, so what do you take the derivative of to get cosine of x? You take the derivative of sine of x. Okay, so you need plus c, you always need a big plus c because we're doing general solutions. Alright, this one, I've got two different things, so I'm going to split it up, give them each their own integral. Alright, they both get their own dx here. This I'm going to use power rule, so I increase my power by 1. Also divide it by that 5. Okay, so to check, I'm going to take the derivative and make sure I get this. If I take the derivative, I drop the 5. That cancels, drop the power by 1. I get x to the 4th. This one is still a power rule. Just remember that square root of x is still just x to the 1/2. So when I integrate this, okay, I need to increase the power by 1. So 1/2 plus 1 would be 3/2. Okay, and then I need to divide by that same power. But of course, I don't want to have a fraction over a fraction, so I'm going to actually end up multiplying by the reciprocal instead. So I would get 2/3 x to the 3/2. Okay, and if I derive this, I'd drop the power. I'd have 6 over 6, which would be 1. Drop the degree of the power by 1, which would make 1/2, which would give me back to this. So my overall solution to this one is going to be x to the 5th over 5 minus 2/3 x to the 3/2 plus my constant of integration. Okay, next thing, this one, I'm actually going to rewrite it as this. Raise the power by 1, okay, which means it's going to go up to -2. Put that same number down here. So I could rewrite this as -1 over 2x squared plus c. All right, this one is actually a special case, so if we follow the same rule as what we did up there, this would be x to the -1. Okay, if I'm integrating that, I need to raise the power by 1. That puts me up to x to the 0. Okay, over 0, which is undefined. All right, so that's not going to work. This is actually a special case that we'll get to later. I just want to make you guys aware of it, so if you do see this, that you don't think that this turns into x to the 0 or something else. Okay, this is a special case. This is actually the natural log of x plus c. Okay, so if you take the derivative of natural log, you get 1 over x. Okay, but that's a special case, and we'll see that later. So that covers the basics of integration. And that should be enough for you to get through your first assignment.